Okay, I want to start today with a little test. Very simple. I'm going to say two things to you, and you just tell me how they connect. Ready?
Ready. Hit me.
I was starving. I ate a sandwich.
Okay. You were hungry, and that caused you to eat. It's cause and effect.
Right. But notice what I didn't say. I didn't say I was starving, so I ate a sandwich. I didn't say I ate a sandwich because I was starving. I just gave you two totally separate statements. I was starving, period. I ate a sandwich, period.
And yet the connection is, it's instantaneous. You can't help but see it.
Exactly. We do this completely effortlessly. We see this, this invisible thread connecting those two ideas. But for a computer, that invisible thread is a nightmare.
It really is.
It's the difference between a machine that just reads words from a dictionary and a machine that actually understands meaning.
And that invisible thread is what linguists call a discourse relation. It's sort of the glue of language.
Yeah.
Is how an argument flows from a premise to a conclusion, or, how a story moves from A to B.
And usually, teaching a computer to see that glue is incredibly expensive. But today, we are dodging into a research paper that proposes a really clever workaround. It's about teaching computers to play a game, a specific kind of word game, to learn the structure of language all on their own.
It's a fascinating approach. The paper is titled Semi-Supervised Discourse Relation Classification with Structural Learning. It comes from a team at the University of Tokyo Hugo Hernault, Danushka Boligala, and Mitsuru Ishizuka.
Structural learning. Okay, that sounds heavy, but the concept is actually surprisingly intuitive. Before we get to the solution, though, we have to understand why this is such a hard problem in the first place. I mean, we have ChatGPT, right? We have these massive language models. Doesn't AI already know how to read?
It knows how to predict the next word, sure.
Yeah.
But understanding the logical relationship between sentences is a whole other beast. To get an AI to strictly categorize those relationships, to say, this sentence is the reason for that sentence, you usually need to show it examples.
Thousands of them.
Thousands and thousands of examples.
Sure. This is that labeled data problem we always come back to.
Exactly. We call them annotated corpora. Someone, usually a human expert, has to literally sit down with, like, a highlighter and just say, sentence A contradicts sentence B, or sentence A elaborates on sentence B.
And I'm guessing that's not a quick process.
It's incredibly slow and prohibitively expensive. And here's the real kicker. We absolutely have big databases for this. You might have seen mentions of the RST Discourse Tree Bank, or the Penn Discourse Tree Bank.
Right, those are the famous ones, so why can't we just use them? I mean, if the work's already done, why are we looking for a new method?
Because those databases are built on, well, standard English.
Yeah.
Specifically, they're largely built on news articles, like from the Wall Street Journal. They are great if you want to analyze the news, but what if you're a doctor?
Or a lawyer.
Or a lawyer or an engineer.
I see. So the way a journalist writes is completely different from how a legal contract is written.
Precisely. The paper brings up a great example here. Clinical information extraction. If you're analyzing medical guidelines, generic relationships like elaboration or background, they aren't very helpful. You need specifics.
Specifics like what?
Well, in a medical context, you really need to know if a sentence is a permission or an obligation or maybe advice.
Oh, that's a huge difference. You may take 2 pills is permission. You must take 2 pills is obligation.
Right. And you should rest is advice. If you feed that into a generic AI that was trained on the Wall Street Journal, it might just lump all of those under instruction.
It misses the nuance.
Completely misses the nuance.
So if I want my AI to understand, say, medical law, I can't use the off-the-shelf training data. I'd have to build my own.
You'd have to hire doctors to read thousands of medical files and manually label obligation versus permission.
And doctors are not exactly cheap labor. You're not hiring them on some gig economy app for $5 an hour.
Exactly. So you hit this bottleneck. You need custom data for your niche field, but you can't afford to create it. You're just stuck.
And that is where today's paper comes in. Semi-supervised learning. This is the solution they're proposing.
Semi-supervised. It's the middle path. The idea is, what if we take a tiny, tiny amount of that expensive hand-labeled data, maybe just 100 examples, and we combine it with a massive mountain of unlabeled data?
And unlabeled data is basically free. You can just scrape the internet.
In this study, they just grabbed 100,000 sentences from Wikipedia. Totally random, totally unlabeled, just raw text.
Okay, but this is where I get a little skeptical. If I give you a book written in a language you don't speak, and I don't give you a dictionary, reading 100,000 pages of it isn't going to teach you what the words mean. You're just staring at symbols.
Right.
How does staring at raw text help the computer learn the structure of an argument?
That is the million-dollar question. And you're right, if you just stare at it, you learn nothing. You need a way to interrogate the text. You need a task. And this is where the researchers got really clever. They used something called auxiliary tasks.
Auxiliary tasks. Okay, walk me through that.
Think of it like a practice drill. Or, to go back to your intro, it's like a game of hide and seek. The researchers realized that even in unlabeled text, the structure leaves clues. Specifically, certain words tend to hang out together when a specific relationship is happening.
The paper uses a specific example that really clicked for me. It was a sentence about sales, I think.
Right. Let's break that one down. The sentence was, our research shows we sell more of our heavier issues because readers believe they're getting more for what they pay for.
Okay, so logically, we have a cause and effect there. The sales are up because readers like the heavy issues.
Correct. It's a reason relationship. Now look at the words. The pivot point, the obvious clue, is the word because. But there's another clue earlier in the sentence. The word shows.
Research shows because. So those two words, shows and because, they're like a pair. They're the signal flare for this type of relationship.
Exactly. If you see shows in the first clause and because in the second, there's a very, very high probability you are looking at a reason relation.
Okay, so here's what the computer does with that massive pile of Wikipedia text. It scans through and it finds sentences that have these clue words. It finds shows and because, and then it hides them.
It masks them. Yeah, it just blanks them out. So the sentence becomes, our research blank, we sell more issues blank readers believe.
And then it asks the computer to guess what goes in the blanks.
Yes, it treats it as a prediction problem. Can you, the computer, looking only at the context, the words around the blanks, can you predict that the word because should be?
Wait, so by forcing the computer to guess the word because, we're tricking it into understanding the concept of reasoning.
You've got it. That's it. We call this inductive transfer. The computer isn't explicitly trying to learn about discourse relations. It doesn't even know what that is. It's just trying to win this little fill-in-the-blank game.
Mm-hmm.
But to win that game, to correctly guess because, it has to implicitly learn that the first part of the sentence is a claim and the second part is the evidence.
That is wild. It learns the structure implicitly.
It builds an internal map. It starts to realize, oh, okay, when the sentence talks about findings and results in the first half and beliefs or motivations in the second half, the connector is usually because.
And it's doing this thousands and thousands of times across 100,000 sentences. It's just building up this huge library of pattern.
Precisely. And they do this for all sorts of relations, not just reason. They look for contrast words like but or however, elaboration words, condition words. They are basically mining Wikipedia for the architecture of the English language.
Okay, I want to dig into the details of this game a bit more. The paper mentions they have to be careful about how they set up the test. They use positive and negative examples.
Right, yeah. If you only show the computer sentences where the words do belong, it'll just learn to guess yes every time. It's too easy. You have to show sentences where the words are present, those are the positive examples, and sentences where they are not present, the negative examples.
And they found the ratio matters. They capped the negative examples at a 2-to-1 ratio. Why that specific number? Why not, 50-to-1?
Well, think about it like a multiple choice test where C is the answer 99% of the time. Eventually, you stop reading the questions. You just guess C because the odds are in your favor.
Lazy?
The model gets lazy.
Yeah.
If you have too many negative examples, so sentences without the target words, the computer learns that the safest, most accurate bet is to just always predict the word isn't there. It stops trying to analyze the context. By keeping it at 2-to-1, you force the model to actually look at the words to make a decision.
Okay, so we have this machine running through Wikipedia, playing hide and seek, getting smarter at predicting these structures. It generates a massive amount of data about how words connect. But we can't just dump all that raw data into our final AI, right? It would be way too messy.
It would be a disaster. We call it the curse of dimensionality. If you have too many features, too many of these little variables, the model gets confused. It starts seeing patterns that aren't really there. It's like trying to listen to 1,000 people talking at once.
So we need to filter the noise.
We need compression.
Yeah.
The researchers use a mathematical technique called SVD, singular value decomposition.
Okay, SVD. I always struggle with the math here. Can we use an analogy? Like, what is SVD actually doing to the data?
Yeah, absolutely. Think of it like making a reduction sauce and cooking. You start with this huge pot of liquid. That's your raw data from the Wikipedia game. It has all the flavor, but it's watered down with a lot of noise.
Okay.
SVD boils it down, It evaporates the water, the irrelevant details, and leaves you with this thick, intense concentrate.
So we go from 100,000 specific little lessons to what?
In this paper, they boiled it all down to just 50 features.
50. That seems incredibly small.
It's super compact.
Yeah.
But those 50 features represent the essence of the structural patterns they found in Wikipedia. They're the 50 most important rules or signals the computer learned about how arguments are constructed.
So instead of memorizing every sentence in Wikipedia, the AI just memorizes these 50 golden rules of language structure.
Exactly. And then, and this is the final step, they take those 50 golden rules and they hand them to the main AI, the one we actually care about, one we're trying to train on that small set of, say, medical data.
So now when that AI looks at a medical text, it's not starting from scratch. It has these 50 intuitions about language structure to help it out.
It has a huge head start. It's like sending a student to medical school who has already read the entire encyclopedia. They don't know medicine yet, but they know how to read and study and analyze text better than anyone else in the room.
Okay, the theory is great. I love the idea of the reduction sauce, but does it actually work? Because in AI, there are so many cool ideas that just fall apart when you actually run the code.
It works. But the way it works is really interesting, especially for people who are dealing with that data scarcity problem we talked about.
Right, the I can't afford a team of doctors problem.
So they tested this against a baseline, just
Right.
a standard AI with no Wikipedia training. And they tested it on the standard data sets. And the magic happens when the labeled data is small,
How small are we talking?
tiny. Around 100 labeled instances. In the world of deep learning, 100 examples is basically zero. A model would just guess randomly with that little data.
And how did this structural learning method do?
It improved the F-score, which is the main measure of accuracy,
Yeah.
by over 100% compared to the baseline.
It doubled the performance.
Doubled it. It took a system that was essentially useless and made it viable. And even when they went up to 1,000 labeled instances, they still saw an improvement of at least 50%.
That is massive. That's the difference between a project failing and succeeding. If I can get a working model with just 500 or 1,000 labeled documents instead of 10,000, that saves months of work.
Exactly. It democratizes the tech. It means you don't need a Google-sized budget to build a custom language analyzer for your field.
But there was a limit, right? You mentioned a plateau in the notes.
Yes, and this is important to understand. As you add more and more labeled data, the advantage shrinks. Once they hit about 10,000 labeled examples, the lines converged. The semi-supervised method wasn't any better than the standard one,
Why is that?
because eventually the computer just learns enough from the direct instruction. You know, if I explain the rules of the game to you 10,000 times, you don't need to rely on your intuition anymore. You just know the rules.
The golden rules from Wikipedia become redundant.
They become redundant.
Exactly. So this isn't a technique you use if you're swimming in data. This is a survival technique for when you are starving for data.
Precisely. It's a specialized tool for low-resource environments. Now, I want to pit this against the competition. The paper compares this structural learning method to something called co-occurrence. This was the previous state-of-the-art, right?
Yes, and interestingly, it was actually developed by the same research group a bit earlier.
So they were basically trying to beat their own high score.
Essentially, yeah. The co-occurrence method also used unlabeled data. But it worked differently. It just looked at correlations. Hey, when feature A shows up, feature B usually shows up too.
Just simple correlation.
Right. But the problem was that reduction sauce step we talked about, or really the lack of it. The co-occurrence method didn't reduce anything. It just added more and more and more features. It just exploded the feature space.
So it got bloated.
Massive bloat. It made the model really heavy and slow. Our new structural learning method with a SVD compression keeps the model tight and fast. Just those 50 features.
But is there a downside? I mean, usually when you compress things, you lose something, or you pay a price somewhere else.
You do. And the price here is data hunger for that pre-training phase.
Explain that. The researchers found that the structural learning method is a bit of a diva. It needs a lot of unlabeled data to work. If they only fed it 10 or 100 Wikipedia sentences, it just failed completely.
It couldn't learn the auxiliary tasks.
Nope. Because if you only read 10 sentences, you probably won't see shows and because together at all. You can't learn the pattern if it isn't there to begin with.
Okay, that makes sense.
The old co-occurrence method could actually squeeze a little bit of value out of small amounts of unlabeled text. But for this new method to really shine and beat the competition, it needed the full 100,000 sentences.
So the trade-off is you get a better, faster, smaller model if you're willing to process a giant pile of raw text first.
Which, honestly, in 2026 is a trade-off most of us are happy to make. Downloading a gigabyte of text is easy. Labeling 1,000 documents is hard.
That's a really good point. We're trading computational power processing Wikipedia for human labor labeling data, and computers are cheaper than humans.
That's the economic argument for this entire paper right there.
So, zooming out. We have a way to teach computers the glue of language by letting them play word games with Wikipedia. It solves the expensive expert problem. Is the case closed? Can computers now perfectly understand everything we write?
Oh, I wish. No. The authors are very honest about the limitations. And the biggest limitation brings us all the way back to where we started the show.
The sandwich.
The sandwich. I was starving. I ate a sandwich.
The implicit connection.
Right. This entire method, the hide-and-seek game, the word pairs, it relies on explicit cues. It relies on finding words like because, therefore, but, however.
But if I just put two sentences next to each other and imply the connection, there are no words to hide. There are no words to seek.
Exactly. If the clue isn't written down, this system is blind to it. The paper notes that while they crushed it on explicit relations, their performance on implicit relations was still, well, modest.
Modest is a polite academic way of saying not great.
It is the hardest problem in NLP, natural language processing. To understand implicit relations, you don't just need language skills. You need world knowledge. You need to know that hunger leads to eating. You need to know that rain leads to wetness. That isn't in the grammar, that's in the logic of the universe.
So the machine can read the syntax, but it doesn't have common sense.
Not yet. That is the holy grail. Teaching a machine to read between the lines, that requires a level of inference that goes way beyond just statistical patterns in text.
Well, that sounds like a perfect setup for a future deep dive. But even with that limitation, this feels like a huge step. Just the ability to spin up a custom classifier for medical or legal texts without breaking the bank. That opens up so many doors.
It really does. It allows us to apply AI to the long tail of problems, the niche-specific, messy parts of the world that aren't covered by the Wall Street Journal.
It's almost like we're teaching the computer to teach itself. We give it the raw material, we set the rules of the game, and we just let it figure out the blueprints of language on its own.
And it turns out, with enough Wikipedia articles and a good game of hide-and-seek, it's a pretty fast learner.
I will never look at the word therefore the same way again. It's not just a word. It's a structural beam holding the entire sentence up.
And now, the computers can see the beans too.
Thanks for diving in with us. If you're working on a niche AI problem, maybe stop labeling for a minute and go download Wikipedia instead. We'll catch you on the next deep dive.